And this is going to be for triangles. So does anyone know what similarity already means? Or do you want me to walk through it? Also, Charity, you could turn on your camera if possible.
Wait. Oh, okay. The triangle? Oh, so like it look like it has like the ratio stuff and it has the same angle.
Yeah, exactly. That's what I'm going to go over first. So there's a similarity relation called AA. This means two angles are the same. Between two triangles. And if AA is true, then I'll keep writing. If AA is true, then the two triangles are similar. So for example, let me draw this triangle, and then let me draw a different triangle. It's about this big. Actually, so these two triangles are not the same because one is a lot bigger than the other. But and since I use this the software on Notability, I know that these angles are going to be exactly the same. But let's say you're given a graph and like 50 or 55. And this angle looks like about maybe 95. So in this example, even though the two triangles are not congruent, they are similar because of the AA similarity relation. Let me actually write that down. Okay. And the reason why AA works is because if the first two angles in the triangle are the same, so for example here, 55 and 95, that means the third one is going to be 180 minus 95 minus 55, which equals 30. Similarly, this is also going to be 180 minus 95 minus 55, which equals 30. So this shows, or I'm not going to write this shows, if two angles in a triangle are equal, then the third angle of the two triangles are the same. So the third angle, and also if you want me to pause on like a certain part of the text, let me know. The third angle is the same for the two triangles. This satis this means all angles in the two triangles are the same, which satisfies the definition of similarity. And I'll zoom out and let you guys copy. Does this make sense that if you have two, then you know the third one is the same? If you have two angles that are equal across two triangles, then you know that the third one is the same. Does that make sense?
Yeah, kind of.
Okay. Actually, I'm gonna give you guys another example. Do you guys need me to stay here any longer to copy? I'm gonna go right here and say also if my handwriting is hard to read, let me know. Like you can also I think you can draw on the screen. So if you want to point to something that's like that's that you can't read very well, just like you draw on it and tell me. Yeah, I wanted to add here that the definition of similarity is that all three angles of two triangles are the same. So if you have the AA relation, then you know then that means that two of the angles are the same, but therefore the third must be the same. Let me give you guys an example. Uh, Problem actually. Are these two triangles similar? And I'm gonna draw them, but I don't want you guys to see what technology I'm using to draw. So I'm gonna unshare my screen for like 10 seconds, draw it, and then reshare it. Okay. I finished on the okay, here's your two triangles. Are these two triangles similar? Sorry. You could shout out the answer or the put in the chat, like it doesn't matter.
No. Wait, 180. Forgot.
What?
Wait, is that 40 on the top?
Oh yeah, that's 40. Yeah, sorry about that. Yeah, it's not really cool. Yeah,
Oh,
Oh, then yes.
yeah. It is
exactly. Yeah,
40, it's yes.
yeah, because you can look at this one is 180 minus 40 minus 70 equals 70. But since you know that this 70 and this 70 are equal to this 70 and this 70, then by AA, let me write this in black actually. AA relation, the two triangles are similar. Okay, now does anyone have questions about similarity?
No.
Okay, sounds good. There's also another definition of similarity that's based on the side lengths in the two triangles. And there's not really like a strict name for this. Or never mind. There is. This is called SSS. Oh, also, let me write that here. Angle, angle. But all the S is a side. Whenever I write like S in a congruence or similarity relation, it's going to be a side. And when I write A in a congruence or similarity relation, it's going to be an angle. Does that sound good?
Mhm.
So SSS is side, side, side. And what this is that the ratios of the side lengths are the same for all three of two triangles, the same for all three sides of the two triangles. And as an example, you could have this. So I'm gonna change the shape of the triangle. I don't want to all draw. I don't want to draw like triangles that all look the same. So I'm gonna make it like this. Actually, no. Let's have one of these grid lines that you can see on the screen equal one. So let's say so we're gonna have, if you can see each of these grid lines, how long is this side length of the triangle?
3.
Yep, 3. What about this? Sorry.
4.
Yep. And what about this one? Last one.
4.
Okay, this one's a really special triangle. You see here, there's a right angle, right? So this is actually a right triangle. And this is a 3, 4, 5 triangle. And this is because 5 equals the square root of 3 squared plus 4 squared from the Pythagorean theorem from last time, remember?
Oh.
Yeah. And even though it looks like this hypotenuse looks like it spans 4 horizontal like grids on the paper, right? It actually is 5 because when you have a diagonal line, it's actually longer than a flat horizontal line. Okay. Does that make sense?
Mhm.
Now, what would the side lengths be of this bigger triangle, just based on the grid lines? What would this one be? This one right here.
6.
Yep. What about the one below?
7.
You count again?
7.
It's one more. Or wait, oh, you're right, you're right. Oh, that's actually, I did draw that incorrectly. What about this?
8.
Yeah. And then now what's this long one? The hypotenuse. You can use the Pythagorean theorem, or you can think about similarity.
10.
Yep, exactly, yeah. And you can also see that using the Pythagorean theorem, whether or not you used it, 10 equals 6, the square root of 6 squared plus 8 squared. So now you can look at the ratios. So you see that 3 over 6 equals 1/2. 4 over 8 equals 1/2, and 5 over 10 equals 1/2, right? And these are all the same. So the triangles are similar. Does this make sense? That the ratios of the side lengths, you look at the side length of the smaller triangle corresponding to the ratio of the smaller side length to the side length to the corresponding side length of the bigger triangle. So for example, 3 to 6, 4 to 8, 5 to 10. You can also reverse the ratios. You can analyze this way. Like 6 over 3 equals 2, 8 over 4 equals 2, and 10 over 5 equals 2. So it doesn't matter whether you're dividing like a smaller side length over a larger side length, or you're dividing a larger side length by a smaller side length. It just matters that you're comparing it consistently across the two triangles. Does this make sense?
Mhm.
Okay, that's good. And also, look, let me show you some angles. So obviously you see the two right angles here, right? Like this one, right? And this angle right here is also a right angle. Also, let's say I draw this green angle here and this green angle here. They're also the same angle. So how else could you argue that these two triangles are similar if you have two of the same angle?
AA.
Exactly, yeah, AA. This shows that you can use both SSS or AA or AA to prove the same thing, that the two triangles are similar. Let me write that down. However, so you see how AA just has two angles, but SSS has three sides? You might be wondering if we could try SS. So I'm going to put that in a little box. The answer is no, you cannot do just SS. And I'll explain why. Hmm. Okay, I'm going to draw two triangles. The side lengths might not be totally exact, but let's say you have this is 3, right? And this is 4. Let's say you also have this is about 3, and the bottom side of the triangle is 4. And that means the third side of the triangle is not the same. So even if you have two sides that are the same, depending on the angle between the two sides, because the two angle is different, then the third side is also different. Does that make sense?
Yeah.
Mhm.
All right. Now we're going to move on to congruence. Does everyone know what congruence means strictly?
Like the same.
Exactly, yeah. Congruence. Two triangles are exactly the same. They have all the same side lengths and all the same angles. And then I'm going to teach some congruence relations. And these are relations between the side lengths and angles of two triangles that if they're true, that means the triangles are congruent. So the first one is SAS, just side, angle, side. And you notice how the A is in between the two S's. So that means this angle has to be the angle that's in between the two side lengths. So let me write this down formally. The angle between, and I'll also draw a diagram to demonstrate. Are exactly. So let's actually use this one. Oops. So you see in these two triangles, in these two triangles, you see that two of the sides are the same, the 3 and 4, and the angle between them is also the same. So this shows that the two triangles are congruent. And it definitely looks like these two triangles are congruent, right? Like they look exactly the same. And the reason why side angle side congruence relation works is because if you have two sides and the angle, then the two sides plus the angle determine what the third side is. Does that make sense?
Mhm.
Okay. Oops. And in terms of pacing right now, is it too fast, too slow, just right?
Just right.
Just right.
Okay. Now I'm gonna move on to next one, which is ASA. And it makes sense when I say two sides and the angle between them, right? Like this angle is in between like this side and this side, right? Does that make sense?
Mhm.
Yeah. So angle side angle is really simple, but it's kind of flipped in terms compared to side angle side. Side angle side. So it's gonna be two angles and the side between them are exactly the same. Just gonna copy that so I don't waste time. And for the example, turn this red. The example I'm going to use is let's assume actually that we don't know this is 3, but we know that this is about 48 degrees, and also that this is about 48 degrees. And also now this is 48 degrees, and this is 48 degrees. So you see that these two 48 degrees have these two 48-degree angles are the same between the two triangles, and the side length in between them, which is 4, is also the same. So this also guarantees that the triangles are congruent. Does that make sense?
Yeah.
And just like with side equals side, how if two side lengths and the angle between them are congruent, that sets the side length of the third triangle, or it locks it. You can't change the side length of the third side length of the triangle if you already know what the two side lengths and the angle between them are. There's a more advanced law called law of cosines, but I don't that's not really you won't have to know that for the AMC8 level. Well, if you're interested, I'll just write it down if you want to take a look at it in your own time. It involves some trigonometry, but force the well, I wouldn't say force. Two sides and the angle between them, like confirm the third side length. Or not even the side. According to the law of cosine. I'm just gonna highlight this. And because two sides and the angle between them, the third side length. If the two sides are the same and the angle between them is the same, then the third side length will be the same. And I can just write this. I'm actually gonna explain this in terms of the diagram. But basically, like the side length C is the side length that's opposite the angle C. The side length A is the angle that's opposite the angle A, and the side length or the side length lowercase c is the side length that's opposite the is the side length that's opposite the angle uppercase C. The side length lowercase a is the side length that's opposite the angle uppercase A, and the side length lowercase b is the side length that's opposite uppercase B. And but in general, you don't have to worry too much about this. I'm just gonna put it down just because uh it's a good proof. And it's actually very similar with ASA, but you're gonna have this if we just two sides. Wait, Cherry, are you still there?
Mm-hmm.
Okay. And this is okay. Aside from the law of sines and the law of cosines, does everyone understand ASA and uh SAS?
Yeah.
Mm-hmm.
Okay. Then we're gonna we have one more, and this is gonna be SSS, side side side. And it's similar to the relation one, the similarity one, but it's that all three sides of both triangles are exactly the same. And for example, I'm just going to go back to the example of the 3, 4, 5 triangle. And this is because there's a really unique quality of a triangle, which is that if you have 3 side lengths, you can only form one shape. Let me write that down. 3 side lengths can only form one shape for triangles only. But this is not true for 4 side lengths. I'm going to use an example. Quadrilaterals. For example, you can have a square of side length 2, right? This is like, but you can also have a rhombus side length 2. Right? But on the other hand, for triangles, if you have a 3, 4, 5 triangle, it has to be this right triangle, 3, 4, 5 right triangle. There's no other shape that you can bend it into. And just to show how you can use SAS, ASA, and SSS, all different methods to prove the same goal, which is that the 2 triangles are congruent. Can both of you tell me what these 2 angles are in these 2 different triangles?
What? Wait, can you say that
Right
again?
angle?
Yeah. Sean, I asked, what are these 2 angles in these 2 triangles that I've highlighted?
Oh, right.
Yeah, you say 90, right? And you see now that you have 1, 3, and 4, which are 2 sides that are congruent, and then you also have this angle that's congruent. So what type of congruence is this?
SAS.
Yeah, exactly. So it shows that. So this is just to show that you can use SAS. You can also use ASA, or SSS to all prove that triangles are congruent. Does that make sense?
Mm-hmm.
All right. Let me write that down. You only need to prove you only need one. You don't want to waste your time proving 3 ways. Okay. Now there's actually a bad one. And this one is called SSA. And it does
Right.
not. Side, angle. I'm gonna draw a frowny face because this is not a good congruence. An SSA is that two sides and an angle that is not between them. Two sides are congruent. Or let's say. And the reason this is so is I'm gonna give you guys example of SSA, but not congruent. Okay, so let's have this side is 4. And you want this angle to be like about 20 degrees, right? And let's say you want a side to be about 3. Right? And when I draw this 20-degree angle, although it doesn't have, like, you know how an angle is supposed to have two sides, right? Right?
Yeah.
But basically, this angle is supposed to, you don't know how long the third side is because the SSA means that you don't know if the third side is congruent. So I should honestly draw like, I should draw a dotted line to show that you don't know what this third one is. It's unknown. So this would be about right, right? But what happens if you, and you can also see that the, when I say SSA, you have the side lengths 3 and 4 that are known. The A is it's basically on the edge of this side length 4. It's not in between 3 and 4, it's on the edge. Does that make sense?
Mm-hmm.
Yeah, and let me actually, this is not 20-degree angle. This is like 35. So let me redraw this. So you probably won't need to know this for AMC8, but it depends on the third angle. It depends on the relationship between the third angle and the two sides. But for now, let's just say that the third angle we're just gonna treat SSA as a bad case. This is about 20 degrees. Let's say you wanted to have this triangle. And you can extend this. You see how this is still 3, 4, a side length 3, a side length 4, and then 20-degree angle. But are these triangles congruent?
No.
Exactly. These triangles are not congruent. So does that make sense? Why SSA just doesn't work? There's actually sometimes there's the
It- Never mind.
Wait, Sean, tell me. Don't be afraid to like ask a question or anything
I'm not sure, so
about SSA.
no, it's like I'm just like let's see.
Wait, what do you mean?
It's okay.
You should. I don't want you to leave the class with questions that you didn't get the chance to ask.
Like I'm not sure why.
Why SSA doesn't work?
Yeah.
Okay, so you can prove that something doesn't work by providing a counterexample, right? Let's say, or okay, using this SSA as an example. Let's say if you want to prove that SSA doesn't show congruence, find an example called counterexample. And it's called the counterexample because it counters the fact that SSA might be able to be used to show congruence. Let me actually make this closer. Where SSA is true, but the triangles are not congruent. Okay. Does this make sense? In a proof, Sean?
Okay.
Huh? They're basically saying like if you want to prove that something doesn't work, then find an example that it doesn't work. Or let's say there's very it's not even a math example. Let's say someone told you water can float. Let's say you can have a glass of water and you tip it and the water can float. Okay. How would you show that the water cannot float?
Doing a test.
Yeah, doing a test, and that test would be an example that water cannot float, right?
Yeah.
Because you would take the glass of water, flip it, and the water would just sink, or not sink, it would just fall down and splatter everywhere, right? So that would be an example. That test would be an example to show that when your friend said water can float, the statement that your friend said that water can float is not true,
Yeah.
right? Now let's apply this to SSA. The statement is that SSA can prove triangles are congruent. So we do a test. And here's the test. This is the test. So we try SSA, and we realize that SSA is true in this test that I've circled, but the triangles are not congruent. Does that make sense?
Okay.
Do you get it more now?
Mhm.
That SSA that the triangles are not congruent.
Yeah.
Okay, Wait, Sean and Cher, do you guys have any questions about these congruences?
No, not more.
Yeah, what about you, Cherry?
Yes.
And also like but Sean, that makes sense, right? Like the example I
Yeah,
said,
that
so,
makes
yeah,
sense.
of like proving you do a test to show that it's not true. That test itself is like the example that it's not true. Flipping water, or someone says humans can fly, right? So I don't know. I mean, obviously, don't try this, but like, let's say yeah, your friend tells you humans can fly, and no, how this
Um,
your friend tells you that apples can fly. Okay, so I didn't want you to like jump off or something, and like that's a bad example in terms of saying like, oh, you can jump off and show that you can't fly. But that's a bad example. Like you'd hurt yourself. So let's say I have an apple right here. It's so old. I don't even. It's like it's like a month old, and I don't want to eat it. Or let's say my friend Ben says that this apple can fly. Like I'm gonna throw it up and it can fly. But what I do is I'll literally just do it right now. Like it can't fly because of gravity, but it can't fly. But that's an example that what Ben said is false. And you can apply this to math and geometry, especially. Does that make sense?
thanks.
Okay. Now there's one more part in this unit. There's this something called the angle bisector theorem. And the proof of this is based on trigonometry, but in terms of what you need to know for the AMC8, you just need to know this is true. Honestly, you practice the problems of it so that you can memorize it. And I'm going to give you a few practice problems. I'm going to first draw this diagram. And we're going to have A, B, C, D, and AD is an angle bisector of angle A. So that angle CAD is equivalent to angle BAD. And you can use this equal sign with a squiggly over the top to show equivalence. But on the AMCA, it's not really going to matter. It's just multiple choice. You just got to know whether something is equivalent or not. Okay. And the theorem says that if AD is an angle bisector of angle A, then uh, the ratio of BA over BD will equal the ratio of CA over CD. In other words, the ratios of the two side lengths around the angle divided by the portion of the third side length between a side length and like the where the angle bisector intersects it is equal. But I think it's better just to show it this way. Okay. And actually, and this is just once you start doing trigonometry in later math, then you can find a pretty easy proof to this. But in terms of AMC8, you honestly just have to memorize this. Okay. So I'm going to give you some examples. I'm just going to be drawing the same triangle. So the numbers might not be totally accurate in terms of how many grid lines they are, but let's say 9, 6. If AD bisects angle. No, let's say if measure of angle CAD equals 40 and actually no, not even 40 equals measure of angle BAD. What is X? I'll give you guys about like a minute to solve it, and then I'll start going through it. And let me show the origin. Let me rewrite this little meter. How would you use the theorem? I'm gonna start writing it. Let's say we have BA over BD equals CA over CD. And BA equals 9, we can write 9 over 6 equals 15 over X. And we know this because measure of angle CAD equals measure of angle BAD, which means that AD bisects angle. I just wanted to express it in a different way to make you think a little more. Does anyone know what X is here?
Ten.
Yeah. All right. Does that make sense how I use this theorem?
Yeah. Wait, will you send you the note later, right?
Yeah, well, I will. Yeah, yeah. Wait, can you guys put your emails in the? I wasn't able to collect your emails last time because I had to rejoin the Zoom, so it actually didn't save. But can you type it right now and I'll write it down? Yeah, and I'll send you last week's notes too. That's my bad. I think like it just didn't save, but I'm putting it in a. And I'll put the websites too, like the Zetamac for arithmetic game, and then art of problem solving past tests, and then but- okay, that should be good. I'll send you those, and then
Thank you.
huh?
Just say thank you.
Wait, what?
Thank you.
Oh yeah, yeah, of course, yeah, yeah. Right. Let's do another one. Okay. What is X in this? And just take a minute to solve, and then we can have a break.
Uh,
It's gonna be hard to do in your head. I don't think I can do this in my head.
Wait, can I write on it?
Oh, sure, yeah, 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 sure. Why not? And Cherry, also feel free to do that if you find that helpful.
Wait, can we write on the?
Yeah, of course. Yeah. I said that didn't
Wait,
work.
but we can't. You need to allow us.
Okay. Okay. Let me do that. Sorry, I did not.
Wait, so
Wait, I'm only not this way.
so it's 8 over x equals to 15 over 17 minus
Yeah.
x, and then use the butterfly
Yeah.
method.
But if I'm yeah, sure. Yeah. Yeah. That's right. I'll just write that. How about you tell? Right now, I don't know how to do it. You can just tell me what to write, and I'll write it.
So, wait, can I? Yeah, like that.
Yeah, butterfly method, right? So wait,
And then, yeah.
I need to make this neater. Yeah. 136 minus 8x, 10x. Yeah, and
Wait,
then
36? Is that 8? Oh, that's 17. Okay, my
17
bad.
times 8, yeah. But that's like that was something you'd be expected to do in your head on the AMC 8.
Oh, okay.
And I'll put that website for the arithmetic practice. And you guys are pretty young, so like you'll get really a lot better really fast when you do it compared to someone like me. So Sean, can you continue, or is Cherry also? Can you continue telling me what to write?
So, and then like 15x plus 8x,
Yeah.
which is, wait, don't write that. Which is like 23x.
Okay, I'll try like this, right? And then with this x, you don't have to simplify.
X is equals to, I forgot. Wait, I'm done.
Oh, you're good. You're good. Wait. Think about what do you have to do to both sides of the equation to get x?
20, I know the stuff.
Sure, you know what to do?
It's like just divide it.
Yeah,
Like,
exactly. Yeah. And that's your answer. It's kind of ugly, but you can't really simplify it. Because if you go on the calculator,
I'm gonna calculate how.
yeah, no calculator, but yeah, you get this number. Like they're not gonna expect you to know this for the AMC8.
It's like just, should we just write it into the fraction?
Yeah, fraction exactly. Yeah, fractions is perfect. I'll put that there. Keep
Will they ask you like not a fraction?
no. Maybe sometimes they'll ask you to estimate to the nearest like 0.1, but then then you could do like this. You know how to do this, right?
Mm.
Long division and the finding decimals. You know how to do this, right?
That is a really.
They probably won't ask you to do this because this isn't really testing how smart you are or good at problem solving. This is literally what a calculator could. This is literally what a calculator does.
Will they calculate it as like fraction?
Yeah, like the answer that it would not be like A, B, C, whatever. That's what it might look like. But this is just long division, right?
Really long division.
Yeah, and technically you could extend this infinitely. Well, obviously you don't have to. They're not going to ask you to do like 25 digits. This isn't like memorizing pi. All right. Do you guys want to see me do the math trick? Like the multiplying numbers?
Sure.
I'll do a few, and then you guys can have your break. And after that, we're gonna get into length calculations. All right, give me two numbers.
Uh, 17,
Hmm
17.
Oh, it's like 17 squared.
Yeah.
Yeah, that's 289. But yeah, that's also like, oh, remember I told you you gotta memorize some theorems, and that's just like then you memorize it however you memorize anything else, like by practicing repeatedly and doing practice problems. Like you want to memorize, okay, like one squared is one, two squared is four, three squared is three, four squared is 16, five squared is 25, six squared is 36, seven squared is 49, eight squared is 64, nine squared is 81, 10 squared, oops, 10 squared is 100, right? And that's pretty easy to know, but you want to keep going. You want to know probably up to like 20 or 30. So do you know 11 times 11, 121, 12 times 12, 144, and maybe that's your times tables. Then you get 13 times 13 is 169, 14 times 14 is 196, 15 times 15 is 225, 16 times 16 is 256, 17 is 289, as we just said, 18 times 18 is 380, 324, 19 times 19 is 361, 20 times 20 is 400, 21 times 21, I'll go up to like 40, is 441, 22 times 22 is 484, 23 times 23 is 529, 24 times 24 is 576, 25 times 25 is 625, 26 times 26 is 676, 27 times 27 is 729, 28 times 28 is 784. Oops. 784, 29 times 21 is 841. Oops. 841, 30 squared is 900, 31 squared is 961, 32 squared is 1024, 33 squared is 1089, 34 squared is 1156, 35 squared is 1225, 36 squared is 1296, 37 squared is 1369, 38 squared is 1444, 39 squared is 1251, and 40 squared is 1600. But that I would say like if you memorize up to like 30, then that's just memorizing. I feel if you do enough problems where you're using a lot of squares of numbers like that, like you'll end up memorizing it pretty easily. All right, now I took way too long for the break. Now you guys can have like a break. Let's come back around like 9:12. Yeah.
Same.
And I'm gonna go back, put this back. If you want to, if you didn't get a copy or something, just gonna leave this on for you guys to look at. Or if you want to zoom in, whatever. Is everyone back?
Oh, back.
Yeah.
Okay, so let's talk about length now. And there's actually a really important connection between similarity and length. And I already talked about this in some examples, but let me just write it and set it in stone. So if two polygons, which are just shapes, and I'm saying polygons because it applies to triangles, but also shapes with more sides than three. Like triangles have a similarity ratio k, and k is like a random number. Then the side lengths of the two polygons will differ by a ratio, okay? In other words, the side lengths of one polygon will be k times the side lengths of the other one. So what this is kind of saying is like, let's go back to the example of the 3, 4, 5 triangle and the 6, 8, 10 triangle from very early on, right? And then you have k equals 2, right? Because you have 6 equals 3 times 2, 10 equals 5 times 2, and 8 equals 4 times 2. You can also say, or k equals 1/2, because 3 equals 1/2 times 6, 4 equals 1/2 times 8, and 5 equals 1/2 times 10. However, for areas, I'm actually going to copy this so I don't have to like spend time writing it again. If two polygons, like triangles, have a similarity ratio k, and where k is a random number, then the areas of the two polygons will differ by a ratio of k squared. In other words, this, the area will be k squared multiplied by the area of the other one. And let's go back into here. So what's the area of this first triangle? You can just shout it out. if your area equals base 1/2 base times height, right? And what's the base?
4.
Yeah. What's height?
Times 3.
There's 6. Now the area for the yeah. What's the base?
8 times 6.
And you see that 24 over 6 equals 4, which equals k squared. If we k equals 2, 20, but or you could have 6 over 24 equals 1/4, which equals k squared. If we let k equal 1/2. So do you see how the area and side lengths, the ratio of the areas versus the ratio of the side lengths is going to be different. The ratio of the area is going to be squared. So the ratio of the side length squared. And the easiest example to see is like a square. This. And then I don't know what's wrong with the square. Let's say you have this square, this first square of side length 1 versus the second square of side length 2. So you can see that the side lengths are doubled, but the area is quadrupled. And you can apply this logic for any shape. Does that make sense?
Yeah.
Sean, does that make sense? Sean, do you have any questions? No questions?
Yeah, no question.
Okay, that's good. Yeah, and then I'm actually going to add something here in green. So everyone knows perimeter is, right? The sum of the side lengths, right? So I'm going to write. So if the side lengths are all multiplied by k, then the sum, if you add all those side lengths that are multiplied by k together, then it's just going to equal k times the sum of the original side lengths. So let me write that down and also do a demonstration. The perimeter. So what's the perimeter of this one? This 3, 4, 5 triangle?
12.
Yeah. And what's the perimeter of this one?
24.
Yeah. So you see that 24 or you can have 24 divided by 12, which is 2, or 12 divided by 24, which is 1/2. And the reason I'm allowing k to be both big and small, that actually might make it a little bit more complicated, but it's because even though when I say like the side lengths of one polygon will be k multiplied by the side lengths of the other one, k can actually be a smaller number. Like you can think about k as either enlarging, making a polygon bigger, or shrinking and making a polygon smaller. But no matter whether it's making them larger or smaller, it's still going to be the same. Does that make sense? Okay, so now let's move on to some other stuff about length. So there's actually an important thing about triangles called triangle inequality. And this is the sum of two side lengths of a triangle is greater than the third side length. In other words, let's say you have this triangle. There's A, B, C. You could say A plus B is greater than C, C plus B is greater than A plus C is greater than B. Does this make sense just when you look at it? For example, that A plus C is greater than B. Because if it's not, let's say, and Sean, this is another example using a counterexample. The triangle inequality is not true. Then we could have A plus B is less than C, but then this would create a really weird triangle. You would have like a triangle that looks like this. You have A, B, C, but like because A plus B is less than C, then A and B are too short, basically, to make a triangle. And this is not a triangle. Example is like, let's say you had a triangle that was like C is 5, and then you had like 1 and then 1. Like this can't be a triangle. And you see that 1 plus 1 is less than 5. Does that make sense? Like I don't know what this shape is. This is just like 3 lines, but they don't connect and form a triangle. Right? And in the case where so, A plus B cannot be less. But let's also see what if A plus B equals C. Because technically then A plus B would still not be greater than C, right? If A plus B equals C, A plus B is not greater than C. But then you would basically get a line. Let's say you would get that like okay, so everyone sees C here. I'm gonna draw over C, and actually no, I'm gonna draw over it with like a thinner font. So you would just get like this, and then let's say you have green for C. And sure, it's really hard to see, like especially if you zoom out. But is this a triangle?
No.
Yeah, well, this is just a line. So cannot equal C. This means A plus B must be greater than C. We can apply this logic to the other three sides, to like B plus C or A plus C, to show that A plus C must be greater than C. Or B, sorry. And A plus or B plus C must be greater than A. Does this triangle inequality make sense?
Yeah.
Okay, now I'm going to give you a set of three numbers. Tell me if they can be a triangle. I'm going to give you like five, and then can you guys private message me on the Zoom? Can 3, 4, 5 be a triangle?
No.
Why?
Wait, yes.
Yes, it can. Yeah,
Wait, 3, 4, 5 is you just plus the like two smaller number together to know.
exactly. That's actually good. That's actually a really good point. Yes. Let me write that
So
down.
if the two small number is bigger than the uh other two numbers, it is like a
Yeah.
triangle. But if the two small number is equal or smaller than the bigger or longer number, it is like cannot form.
Exactly. That's a really good observation, Sean. Two more than the third. Because the largest plus one of the smaller ones will always be larger than the other smaller one. So this is a yes, right? What about the second one?
The second one? The
Yes.
second one? No. No.
Yeah, it's no, because
like 3 plus 4 equals 7 and 7 is smaller than.
exactly. What about the third one?
The third one?
Yes.
No. Wait, I don't know. Wait, is it 4 plus 7?
Wait, what? Which
Is
one?
it no? Isn't it? Oh, yeah, it is. It's
Yeah,
11.
because you 7 plus. Apologies if I had bad handwriting. Let me know also.
Oh, it's okay. It's not as bad as mine.
And at least it's good that you don't have to hit your handwriting on the AMC8. What about the fourth one?
Fourth one, it's
No.
Yep. What's the last one?
No.
Yep, because 2 plus 1 is less than 4. What about this one? Hmm. What happens if you add those numbers? Oh, no, sorry. This is actually because you don't want negative sign numbers. Let's see it. No. Hmm. Can these make a pair? Maybe make it a triangle?
Yes.
Or think try again, try again. How about this? So let's assume
wait,
these, yeah.
Yeah, wait. Is it like no?
It's no. And why?
2x minus 21 plus x is smaller than 20 minus x.
Try a different one. Try different pair numbers. What if you try these two? What would that sum be? What happens if you add 20 minus x and 2x minus 21? I'll add it. I'm gonna first combine the like terms. I'm gonna say 2x minus x plus 20 minus 21, and this equals x minus 1, which is less than x. Does that make sense?
Oh,
Yeah. So like you want to be able to work with the variables as if they're numbers and be like adding them, combining like terms, all that. Okay.